All right, I guess I'll get started. Hello, I'm Alvaro. Um, I'm going to be talking about SWD over USB-C. Yes, acronyms, I will explain them in the first couple of slides. But yeah, so have you ever wanted, if you made a microcontroller project or any other project, have you ever wanted to just do full debug with the same cable you're using to charge, to do data transfer? And I don't mean just serial port doing serial printfs, which is great. That's one form of debug. But some of us firmware engineers like a little bit more. Um, so for those who are not familiar with what SWD means, it's single wire debug. And it's kind of an ARM-specific two-wire interface that's the same as JTAG. So JTAG you can use to read registers, program your device, step through the code instruction by instruction. And single wire debug just lets you do that with a serial two lines. Yeah. And that's a USB-C connector. I know, it's a new fangle thing. So why would you want to do this? So a few years ago, I was working at a company making buoys. So these are weather-sealed devices that get deployed in the ocean for years at a time sometimes. So not super accessible. You could remove the lid, and then inside there's some gaskets, and you can lift those, and there's a USB port to charge the device if you want to charge it indoors, not through the solar panels. And it also lets you pull files from the SD card through USB. When I was the lead firmware engineer, and when the design started happening, I said, hey, I want to be able to do full actual development, step through the code, inspect variables, without having to have a special unit that's taken apart with like wires hanging out, which is usually what we end up doing, or we have a development board. But I want to be able to do this on production units, which is why I was like, hey, we have all these 24 pins in USB-C. Let's add some debugging capabilities. So some of the use cases, there we go. Weather sealed devices, like if you have a device that you only have that waterproof connector, you can do that. Sometimes you have a really small device that you still need the USB connector, and you don't have room for pogo pins for pads where you can use spring-loaded connectors, or TAG Connect. I love TAG Connect, but sometimes you just don't have the space for it. Other times it's just, yes, you can take it apart. You do have room, but you don't want to have to take it apart. And you want to be able to do it on production devices. And don't take my word for it. Everybody's doing it. There's an open source project called Teardown that lets you expose the SWD lines on all iPhones, modern iPhones, right? So Apple is doing this, has been doing this for a long time. Reverse engineers have figured out, with the Lightning connector and also with USB-C, how to get access to these pins. So I have links in the slides, and I'm going to have what do you call is QR codes later on, so you can scan and access to this. All the content in these slides is also on my website. I have a blog and whatnot. So okay, let's really talk about. There we go. Let's talk about USB-C. What do we have to work with? So USB Type-C is just a physical connector. It doesn't tell you anything about speeds. It doesn't tell you about what data is going through it. It's just 24 pins. There is a standard. So you have your old school USB connector. You had 4 wires. You had power, ground, D plus and D minus, just data. In this case, it's kind of redundant because you're able to flip it upside down. And then you have the plug and the receptacle. The plug is what's in your cable. The receptacle is what you plug into it. High-speed USB, like USB 3, uses 2 of these differential pairs. We have access to 4 TX plus, TX minus. This is really small, sorry. This has TX2 plus, TX2 minus, RX2 plus, RX2 minus. It gives you 4 high-speed pairs. So when you hear Thunderbolt cables or DisplayPort, that's what they're using. And unfortunately, not all cables have these connected. All cables do have what's called a CC line. And you'll notice that the receptacle has CC1 and CC2. The plug has CC1 and then something called VCON. It's the same thing. But what happens is a cable only has one of these wires connected. So there is no official USB cable that has both CC1 and CC2. And this is how you're able to tell which orientation a cable is connected. To you and me, it doesn't matter. We can just plug it in either way, and it just works. Inside the device you're plugging into, either they just shorted the pins together, or they're actually doing something with this information. So yeah, Type-C cables will only have a CC line connected. This is how devices can tell. And then I'm going to talk about these resistors, what they mean. But when you make your basic project with USB-C, you put a 5.1 kilo ohm resistor, and then the source knows that it can talk to it. Another thing that happens over the CC line is negotiation of power. So the new power supplies, they don't provide just 5 volts. They also provide 15 volts, 20 volts. This negotiation happens over the CC line. So that CC line tells you the orientation, but it also lets you communicate how much power you're going to want. So go back to the old USB 2. So most projects you and I will work with just have high-speed USB. We're not dealing with super speed, Thunderbolt, all that fancy stuff. So there's a lot of room for activities. There's all these additional pins that our projects, most projects, I would say the majority of hobby or not super high-end stuff is not using these pins. And the connectors have them available. You can get cheap connectors that don't have these, and they're cheaper and easier to solder, and I highly recommend you do them unless you need to do this. But it does give us a lot of spare pins to work with. So I'm going to, I had already started my quick tangent, but I'm going to continue. So USB power delivery, it's part of the USB standard. And like I said, it uses that CC line to negotiate power. Nowadays, they can go up to 48 volts, 240 watts, which is insane on this little USB cable. It does require some intelligence. So either a microcontroller or a specialized IC on both sides to say, hey, can you give me 20 volts at 5 amps? And then the other guy's like, OK, yes, I can. Or I can give you 9 volts at 2 amps. Can you take that? And they have this negotiation. That we're going to ignore that. It is useful, but if your project doesn't care about that, it makes things a lot easier. If you're fine with 5 volts at 3 amps, everything is going to be a lot easier. The other way to figure out how much power a device can take is with, I call it dumb PD, but it's the official name is USB Type-C current. And this is the old school way of, hey, I'm going to have a different resistor, pull-up resistor on the power supply side. And depending on that resistor value, you know how much power you can draw. The default of USB is 500 milliamps, and that's been the case for a long time. Later USB, you can get more. But with this, you as a device can read the voltage in that pull-down resistor that you have and say, oh, can I draw 1.5 amps, 3 amps, or just 500 milliamps? And this works at DC. Like, you don't have to communicate. It's just a resistor value. Technically, it's a current that matters, but you know, if you know it's 5 volts or 3.3 volts, you can just do the math. So that's what I'm going to talk about. All right, so back to debug accessory mode. And I'm going to talk about the correct way of doing things, the proper spec-compliant way. And then later, we're going to ignore all that and tell you how to do it the cheap way. So USB-C, the spec, it's like a hundreds of pages document. And one part of the document has a debug accessory mode. So this whole idea that we're playing with is actually in the spec, or it's allowed by the spec. So remember that both CC1 and CC2, no USB cable actually has both. Well, if you make a custom one that does have both, that would indicate to the device you're plugging into, this is a debug accessory. So do something about that. And then it allows for all these pairs, the TX plus minus, and then even you could repurpose the USB lines, the low-speed, the high-speed USB, and then it has some extra lines. It lets you repurpose those, if you will. You can't do that for the CC lines or for power and ground. Because if you have both CC1 and CC2, if you wanted to figure out how much power you can draw using that dumb PD mode, then you'd have to figure out, OK, which resistor am I looking at? Because now I have 2. So they actually allow for that too, and they have a special lookup table to figure out if you do have both pull-up resistors, which powers you can draw. So they thought about a lot of this. So how do you actually implement this if you want to do this? So I call it arbitrarily selected, I'm going to repurpose these particular pins to do this particular other things. So the bare minimum is you only need two. You need SWD clock and SWD IO. It's all you need for SWD. SWO is kind of an additional nice to have. A reset pin is always nice because you can get your microcontroller in a known state. Not really required. And then I also decided to use the voltage of the target and just an extra ground on this SBU pins, which means when I rotate it, I'll have power on one side or the other, and then I can figure out if it is in the correct orientation. Because now I'm using pins in my own way, it's no longer bidirectional. There are ways to do it that way, but I'll explain why I didn't in a little bit. Okay, so again, proper implementation, how would I do this? I would say, whoops, if I have a debugger connected, my device can then use some switches to connect the debugging signals out to the USB port. Because otherwise, if somebody just plugs into a random thing, you don't want your debugger lines just connected, or your reset line, for example. It might reset your microcontroller, and actually had issues with that at some point. So the proper way of doing this is to use either a multiplexer or just a switch. And this is what like your iPhone will do, right? If your iPhone gets the right incantation over the USB port, it will reroute the main processor's debugging lines straight out the back. But normally, it's actually high-speed lines that are going there. So I was able to use just a simple comparator, or two comparators, to monitor the voltage on those two CC lines, which tells me, hey, this is a debug accessory mode connected versus just regular old cable, and then an AND gate, and I was able to use a switch to connect the signals. So, testing, before you do something, you get some breakout boards, try it out. It works. This is what I was doing to prove to my old boss, like, hey, we should do this. I made many different accessories. So because you need to be able to pull these resistors up and whatnot, I made a little board to do that. So this board passes USB through. So USB data lines go right through. The USB PD line on the CC1 line coming from the power supply gets read by this microcontroller, and then it uses those other two to provide the correct voltages on the CC1 and CC2 line for the target. And then it has an ARM 10 pin, which is a standard, this is a standard port that you can connect your regular debugger into. Let's see. And then, of course, I made some tester boards to be able to verify this, right? And because I have power and ground in that SBU1, SBU2, if I plug it in backwards, it'll say, you're upside down. You need to reconfigure it. And it worked. So this is the controller board for the buoy that I was originally doing this for, and it has my little adapter. Over here, it's the adapter without a debugger connected. You could use it with, without, and many ways. Unfortunately, this is extremely fragile, and I'll talk about that too. But it worked. So it's a nifty way of doing it. So this board has an ATtiny that reads the voltages and sets the voltages. How do I program that one? So then I did SPI ISP, which is the ATtiny programming interface, over Type-C, just for the debugger. And I thought that was just a fun, like, oh, wait, I need to do the same thing to do the same thing. So manufacturing, USB Type-C plugs are a pain in the ass. I hate them. It's a necessary evil if you want to be able to do debug accessory mode, because otherwise you need custom cables. So I hand soldered some. They sucked. I made some, I think, either PCB way, then JLC PCB. I kind of went back and forth. And yeah, it costs more, but this is kind of one-time cost, right? You only need a few of these devices per developer, if you will, and then you don't have to be making that many. Okay, so we've talked about the proper way of doing this. What if you don't care if you're following the USB spec? What if it's just, I want this on my projects just for ease of use, for simplicity? How do I do it? How simple can we go? Extremely. This is a 3-part bomb. I added an LED for fun, but if you ignore certain things, you can get away with this. So this no longer follows the USB debug accessory mode standard, right? Because we, in this case, are going to have to use a USB-C cable to plug in to the debugger, to the interposer board, and to the target. But it means we don't have to deal with USB-C plugs. We don't need a microcontroller to set voltages. We can just pass through the CC lines, and it'll still get the power voltage from the power supply. Unfortunately, oh, it also gives you like flexibility as far as cable sizes. You know, you could get a debugger cable this long, this tiny. The negative sides is your SWD pins will be exposed to the USB port for the world. There's ways to mitigate that. You do need a full-featured USB-C cable because since we're using the high-speed pairs, I usually get these little 6-inch Thunderbolt 3 cables, and then I'm able to connect the targets. But this adds 0 BOM costs on your device because now you can ignore all those multiplexers. Like you don't need to switch the signals in and out. You don't have to have comparators or anything like that. Another thing I found out is all USB-C cables flip some signals. Not all the signals, but some of the signals get flipped. So for example, the high-speed pairs, the TX and the RX kind of get flipped together. So I had to do that flip on my own board on the second version because the first version didn't flip it. So yeah. But yeah, that's a schematic with the extra feature of that green LED that will still tell me if I plugged it in correctly. So because I added that, I still know if it's plugged in the right way. And again, 0 added BOM cost to your target. And this is kind of what it looks like. So now I have my debugger over here. I have that adapter board up there and just a little flat super speed or whatever USB-C cable. How do you know if you're, you know, this little cable here, you need to know if it has all the pins required. That was my last talk at Teardown a couple of years ago. This is an open source USB cable tester. You plug in USB on both sides, and it'll tell you all the pins that are connected. And I designed this out of frustration because there wasn't one that existed, and my dreams came true, and now there's clones of it on Amazon that are better and cheaper. So everybody wins. So here are some examples. I made examples of all possible combinations of how to do this so you don't have to. So at the very top, it's the fancy target debugger that has the microcontroller that does all the things properly. Then on the right, top right, we have the ultra basic version. And then I have 2 example targets. This example target is doing things the proper way. It disconnects the signal when the debugger is not attached. It has those switches. It has a way to detect if it's in debug accessory mode. This one is just a regular, I think it's a Raspberry Pi Pico project, the default with the minimum amount of parts, and it just connects to the USB-C connector. And then I had them all manufactured, so I have JLC examples for anyone who wants to try this. Some other notes. The pinout is whatever you want. There is no spec. Even the debug accessory mode, which is part of the spec, tells you use these lines however you want. So if you wanted to make your own version of this, you could have UART going out the bottom. You could have analog signals going out USB port. You could make it reversible so that if you only use some of the signals, you can make them both ways. So you don't have to worry about the debugger being attached properly. Some Android phones actually already expose serial ports through the USB-C connector, again, with the right incantation. Just be careful, if you do make it yourself, what you expose and how you expose it. The original version of this, for the company, I got the pinout backwards, and I connected either to the TX lines or the RX lines. And when you would use a full-feature cable and plug it into just a regular laptop, it would hold the device in reset, which is not great. So, you know, I had to fix that. But yeah, it's a easy way to be able to debug properly in all of your devices if you're using USB Type-C. Again, you do have to use the full feature connector that has the 24 pins. They're a little bit more expensive, but they're so common that most manufacturers see them all the time, and the manufacturing errors are pretty low. Some wish lists. If I was able to do this myself, like unlimited time and money, I would have a form factor more like this, where you have a custom cable. I could have the actual debugger be part of this, so I don't have an external debugger. We could use a Blackmagic probe, for example. And then it would need to be have both of the debug accessory modes pins in there. But this would be kind of the proper way of doing it. I try to figure out, like, hey, how are these made? Take it apart. The USB cables are actually a little PCB, and just, I don't know if these are hand soldered, but it's kind of an interesting way of doing it. But to do any of these things, you need some higher volumes. Maybe someone here knows cable manufacturers that don't do it so expensive, but I've imagined making a breakout board of a USB-C cable with all the pins, not with both CC, and then make a standard header, and then people can do all sorts of stuff. I mean, all these laptops might have things like that. You know, they have USB-C ports, and maybe there's debug connectors. So having these tools might allow people to play with these things. So anyway, I don't know if we have time for questions, but I'll be around the whole conference. Here's a link to my blog post on this. And yeah, question. Yeah, so the question is putting the V target, the voltage of the target on the SBU lines. So the SBU lines are seldom connected on devices, so I thought it was a pretty low risk thing. But again, it's if you expect, most people are not using the fancy USB-C cables because they're expensive, they're hard to get, and most of them barely have data lines. So it is a risk. But I tested it, and I was like, here's my laptop. Oh, OK, it didn't break. So it was a low risk. You could put a resistor. I might have put a resistor on there, because it's just a reference voltage, really. The only reason to put that is if you have a debugger that scales the voltage depending on the target. If your target's 1.8 volts or 3.3 volts, it'll adapt those signals. But if you control both ends, you don't need that, because you know it's a 1.8 volt debugger, so you don't have to mess your stuff. Any other questions? Yeah, I think they do have to be negotiated. No, the USB, so USB high speed, the USB 3, sorry, super speed, they send these pulses automatically. And that's the reason that I picked either the TX or the RX lines only, and not both, because if you plug in a USB fully featured cable to a super speed capable port, it'll send these quick test pulses. They were small enough that I actually didn't think I would care. But if I plug it into the receive line, the laptop is not going to be transmitting anything on those lines. So that was my trick of why I selected that pin out. I don't know if there's a requirement, but I do know that it will send those pulses every time you plug something in. Any other questions? All right. Thank you so much.